In this lecture, we are going to discuss Holt's linear trend model. Previously, we looked at simple exponential smoothing, and we noted that our forecasts were always a straight horizontal line. Holt's linear trend model extends the exponential smoothing model so that we can capture and forecast trends. Let's start by considering what a linear trend might look like. Well, linear means line. We know that the equation for a line in general is y equals mx plus b. Let's suppose that instead we say y sub t equals slope times t plus y naught. This doesn't change anything. All we've done is replaced x with t and b with y naught. As you know, the coefficient in front of t is called the slope, and the constant term by itself is called the intercept. Clearly, it is the value of y at time t equals 0, hence the symbol y naught or y0. Note that the slope is the amount that y changes when t increases by 1. Understanding this kind of equation is a crucial step in understanding Holt's linear trend model. The best way to understand Holt's linear trend model, in my opinion, is to simply look at the model equations and to try and decipher each component one at a time. The first thing you'll notice is that it's very similar to the simple exponential smoothing equations in component form. That's why it was so important to rearrange them in that way. You'll notice that, whereas the simple exponential smoothing model had 2 equations, we now have 3 equations. So we've added one more equation, specifically one more equation for modeling the trend. So now we have 3 equations in total, one for the forecast, which we already had, one for the level, which we already had, and one new equation for the trend. Let's start by studying the forecast equation. As you can see, this is nothing but the equation for a line. Of course, we now have different symbols, but I know you're not going to let that intimidate you. As before, we have the level, which represents some sort of average value. But now, we also have a term that increases linearly with h, which is the number of steps in the forecast. Clearly, this means that b of t is the trend, or in other words, the slope. That is, L of t, the level, is the starting value of the forecast, and then the forecast increases by the amount b of t for each step into the future that we forecast. Of course, b of t can also be negative, so if you increase by a negative amount, then you're actually decreasing. The key point is, thanks to this new linear trend term, our forecast is no longer a horizontal line, but a line in any direction. This justifies the name, Holt's linear trend model. Let's now study the level equation. Again, this is very similar to the level equation from before. The only difference is on the far right, which represents this moving average value. Remember that the prediction is now made up of 2 components, the level and the trend, which are represented by L and B. As you recall, in order to make a forecast, we find L plus H times B. But since this is just one step ahead, H equals 1, and so the value of our prediction is just L plus B, or more specifically, L at t minus 1 plus B at t minus 1. So that concludes how to update the level. It is still exponential smoothing on the input signal y of t, using L of t minus 1 plus B of t minus 1 as the previous smoothed value. Finally, we have the trend equation. As you can see, the general form of this equation still follows that of exponential smoothing. We have beta times something plus 1 minus beta times the old value. In other words, the trend b of t is also an exponentially smoothed estimate. But what is it an exponentially smoothed estimate of? Well, that's the thing that goes in front of the beta. So what goes there? In fact, it's just L of t minus L of t minus 1. So why does this make sense? Remember that b of t is trying to estimate the slope, or the trend of the signal. The slope of the signal is the value at one time, minus the value at some other time, divided by the difference in time. In our case, the time difference is just 1 because we're updating b of t on every time step. So L of t minus L of t minus 1 makes sense. You might think, why L of t and not y of t? Remember that one way of thinking of a time series signal is that it is noisy. The level L of t represents the smooth version of that signal without the noise. And so taking the difference in L of t is a better estimate of the overall trend because it essentially removes that noise from the equation. Recall that previously, alpha was treated as sort of a hyperparameter that could be tuned depending on what you were trying to do. In fact, this is often the case. For example, suppose you're working as an audio engineer and you would like to remove some noise from a sound file. Well, if you have experience with sound editing, then you probably know that you often have to choose some parameters yourself. You tune these to your taste depending on what the final output signal sounds like. You want it to sound subjectively good, which in general is not something that can be quantified. On the other hand, with Holt's linear trend model, now we're getting closer to the machine learning picture where what we care about is predictive accuracy. We want our forecast to be good, and now that our model can exhibit a trend, it actually has a chance of making decent predictions. Therefore, the parameters that we learned about in this lecture, alpha and beta, will no longer be chosen arbitrarily, but rather we can fit them. As usual, if you're familiar with machine learning, then you know this involves setting up a loss function like the mean squared error, and then minimizing the squared error over the training set using methods such as gradient descent. If you are unfamiliar with this process, then you don't need to worry because stats models is going to do all this work for us. Finally, let's take a quick look at how the code will look at a high level. As before, we start by instantiating the model. Unlike scikit-learn and most modern machine learning APIs, this is where we pass in the data, which is a univariate time series. Unlike scikit-learn, since the data is univariate, it's okay if this data array is one-dimensional. Next, we call the fit function, which in this case doesn't take in any parameters. In scikit-learn, this is where the data would usually go. This returns a result object. We can use the result object to obtain the predicted values from the train set by calling the attribute fitted values. And if we want to forecast, we can call result.forecast, passing in the number of time steps to forecast.